Um, well, let me start the lecture. So today we're going to talk about neutron scattering and magnetic excitations. And primarily for today's lecture, I'll focus on spin wave excitations. Let me introduce myself. My name is Young Lee. I'm a professor at MIT in the Department of Physics. And I study correlated electron systems and quantum magnets. I have studied spin waves, but more recently I'm more interested in studying things that are not as conventional as spin waves. But spin waves are very important, so it's worth having a basic understanding of them. And I understand not all of you are probably experts in magnetism, so I want to make sure that I cover enough of the basics. So here is a brief outline of today's lecture. So I will start with some basics about magnetism and how neutrons can probe the properties of magnets. I will do some simple examples, some textbook examples of spin waves, first starting with a ferromagnetic system, and then something that's a little bit more complicated, anti-ferromagnetic spin waves, but still looking at the very simple cases. And I can't resist having some of my personal preferences seep in to look at a case where the spin waves are a little bit unconventional, and it's in a system that is called a Kagame lattice, which involves geometrical frustration. Okay, so let me just begin by talking about magnetism. Magnets are very important systems in condensed matter physics. They're very good model systems of interacting degrees of freedom. So let's just consider having a collection of interacting magnetic moments. They wouldn't be so interesting if they didn't interact with each other. They interact, and we can ask, what is the origin of their interaction? You could think very classically that any magnetic moment has a dipole field, and that dipole field will interact with another magnetic moment. So there will be a dipole-dipole interaction, these interactions can be of long range, but the magnitude turns out to be very small for the types of magnetic moments that we're interested in on these magnetic ions. So the typical energy scale would be less than 1 Kelvin. So for example, if you're interested in finite temperature magnetic ordering, maybe at room temperature or slightly below room temperature, this isn't a strong enough energy scale to give you that. So what really is the cause for interactions in magnets is exchange, and there are different types of exchange. These are all consequences of quantum mechanics, it's also a consequence of the fact that the electrons are fermions, and they have Coulomb repulsion since they are negatively charged objects. And what we're going to focus on are magnetic ions where it's a magnetic moment due to the angular momentum of the electrons that gives you this moment. So if you have a direct overlap of electron wave functions, you can have direct exchange. There are systems where you could have some local magnetic moments embedded in a sea of conduction electrons, and then the conduction electrons can mediate an exchange, and we call that indirect exchange. And there's also a case where you don't have direct overlap of the electron wave functions, but you can have exchange mediated by a third atom that sits between the magnetic ions, and this is called superexchange. And this will be important in transition metal oxides, which are, you may have heard of. They're very interesting condensed matter systems, such as high temperature superconductors. And for these transition metals, their direct overlap is not extremely large, so it's the superexchange mechanism that can give you substantial magnetic interactions. And in particular, the copper-oxygen-copper bond in these copper oxide superconductors gives you very large exchange energy scale, which can be as large as 1,500 Kelvin. And clearly you can imagine that there'll be some interesting magnetism at room temperature and below. So if you have interactions, well, that normally will lead the moments to order if you cool down to a low enough temperature. And we're very familiar with several types of magnetic ground states. So I'm sure you're all familiar with ferromagnets, where the interaction tends to have the moments align parallel to each other. And ferromagnets like iron have played a role in technology and history for many centuries. It turns out that antiferromagnets are actually more prevalent in the world, and this is the case where the nearest neighbor interactions, for example, could be tell you that the moments want to be anti-parallel with their neighbors. So you don't have a net magnetization, but you do have an ordering in this kind of up-down arrangement. And the theoretical idea that such a state could be a ground state was put forward by Louis Néel in the 1930s, and Cliff Scholl, who was one of the founders of the neutron scattering technique, and probably a hero to many of us, showed with neutron scattering, magnetic neutron scattering, that these antiferromagnetic states do exist in real materials, and that was a real triumph, and he shared the Nobel Prize with Brockhaus for his developments and discoveries. And I would put a third state here, the quantum spin liquid state, because this is a ground state in magnetic systems that, at least in theory, we believe should exist. And it's only recently that we've been studying real materials that appear to have such a state. And in the next lecture, I'm going to talk a little bit about some of the interesting physics there. But what I want to say is that neutron scattering is going to be key to this type of research. Okay, so let's consider the states where you do have magnetic ordering of the spins. And I'm going to use the word spin colloquially. It's the angular momentum of electrons that can give you the magnetic moment, but I'll just call that spin, even though there could be more than just spin angular momentum. So both the ferromagnetic state and the antiferromagnetically ordered states that I showed in the previous slide, they typically break a continuous symmetry. That is, if the spins have Heisenberg symmetry, they're free to point in 3 dimensions in spin space, or XY symmetry, they're free to point in a plane in spin space. So those are continuous degrees of freedom. And if you choose an ordering direction, then you're breaking that continuous symmetry. And then from this ordered state, the low energy excitations we will refer to as spin waves. And the fundamental quantum for these excitations we can call magnons. And just qualitatively, what might you expect from these states? There's an interesting theorem by Jeffrey Goldstone, who's actually a particle physicist, a theorist, but it applies to condensed matter physics. And the idea is that for the very long wavelength spin waves, the energy of these excitations vanishes. And the basic idea is if you start with Lagrangian, we'll probably talk about Hamiltonians more, with a continuous symmetry group, the new solutions have reduced symmetry and contain massless bosons. And just parsing that into our language, massless would be gapless and the bosons are the spin waves. So these massless particles correspond to spin wave excitations in which only the direction of the phase angle makes infinitesimal oscillations. And what you can imagine is that there should be an excitation or rearrangement of the spins where you tilt all of the spins uniformly, so there is no relative phase angle with its neighbors, so there is no energy cost to that, and that should not cost you any energy. And it's when you start creating a phase difference between your neighbors that there will be some energy cost. So let's think about this for a quantum mechanical energy in the Hamiltonian, and let's think about the Heisenberg ferromagnet first. So this is a rather simple case. So the Hamiltonian has this first term, which has this J, which is the exchange parameter, and here it's going to be positive, since I have a minus sign out front for a ferromagnet. So this prefers states where the spins Si and Sj are parallel. And J, in principle, can couple spins beyond nearest neighbors, but very soon I'm going to just restrict this to nearest neighbors. But this is a general Hamiltonian, and then if it's in an applied field, you have the Zeeman energy. Now, this Si dot Sj term here, we can rewrite in terms of the Sz operators and raising and lowering operators. And this is a very standard decomposition. And when you apply this operator on a fully aligned state, and classically that's what we expect, right? If the energy is telling us neighboring spins want to be parallel, then the low energy state will be when all of the spins are parallel and pointing in the same direction. So that's what we classically expect. And we can see when we operate with this Si.Sj operator, this lowering operator will annihilate, and Sc JSI Szy will just give us S squared. So we do have a proper eigenstate. So this also turns out to be the exact ground state. So this fully polarized all up state is a good quantum eigenstate. And there's really no surprise there. Continuing on this, so the ground state is fully polarized. So if we have n spins, the total spin is n times s. So let's think about the excited states. So then the excited states will be the case where you just have 1 unit less for the total spin, so ns minus 1. If you think about this with the collection of spin 1/2 moments, then this would just be having a spin up flipped over to spin down. It's hard to get this on the camera. Okay, this spin flip we can think of being shared by the whole collection of the spins. And there's a nice classical way to think about this, as shown here. And oh yeah, so by the way, these low energy excitations are the spin waves. So in this picture here, in this upper panel is just the ground state where the spins are fully polarized. And then an excited state is when you're sharing one of these flip spins among all of them. So you deviate all of the spins a little bit from this polarization direction. So they all lie on a cone. And now you're free to change this transverse component of the spins, its phase with respect to its neighbor. So you can imagine how that phase changes, what wavelength rearrangement you have for the spins on this bottom panel. That will give you a different energy for that excitation, even though it still has just one flip spin. Different wavelengths will give you different energies. Okay, so we can then calculate for different wavelengths what is the energy for that excited state. And these are some standard calculations you can find in textbooks. For example, Lovesey in Chapter 9 has this. And we use an approximation called linear spin wave theory. And this seems to work very well for a lot of magnets. And what's typically done, and I'm not going to, I want to keep the math to a minimum so you can mostly get the conceptual understanding. But there is a convenient method called the Holtzien-Primakov transformation, where you, instead of using spin operators, you change them to independent boson operators. And you will take some approximations as well and come up with a calculation to leading order for the excitations. So if you apply linear spin wave theory for the Heisenberg ferromagnet, you get the following result. You have the frequency as a function of wave vector is the following. You have the Zeeman energy here, and you have this other term which depends on the script j. The script j is the Fourier transform of the exchange parameter. And now, just to make this a little bit more transparent, we'll restrict this to interactions just between nearest neighbors. So when you do that, this second term simplifies, and you have 2 times z, which is the number of nearest neighbors, js, and then 1 minus this gamma. And gamma is the following here, where this is summed over all of the neighbors, nearest neighbors of one of the magnetic ions. And again, to make this a little bit more clear, we can think about a simple lattice to put this on. So let's put this on a cubic lattice with the lattice parameter a. And in fact, we'll just look at what's happening at very small q near the zone centers. And this reduces to the following form, where again you have your Zeeman energy and the dispersive part, which has some constant d times q squared. It's quadratic in q. And this constant d, sometimes called the spin wave stiffness parameter, is 2js times a squared. And a typical dispersion within a Brillouin zone for the ferromagnetic spin waves, I just drew qualitatively here, where again near the zone center it's quadratic and it disperses up to some high energy at the zone boundary. Okay, so that's some basics about simple ferromagnetic Heisenberg model. And how would we measure this type of excitation with neutron scattering? Now, I know that Colin Broholm has already gone over many of the cross-sections for magnetic neutron scattering. And in Lecture 8, in particular, you saw that the magnetic neutron scattering cross-section, let's go back here, is related to the dynamic correlation function. So for the one magnon neutron scattering cross-section, and so these are the spin wave, the scattering from the spin waves, we saw in this classical picture that it was the transverse component of the moments that we're processing, and that turns out that only the transverse terms in the correlation function, so terms that are like the following, Si plus, Sj minus at some other time t, or vice versa, they give rise to the inelastic scattering. There are longitudinal terms in the correlation function, but they give rise to just regular elastic scattering. So these transverse terms give rise to the inelastic scattering. All right. And let me just give you the result for the cross-section. So you have some of your standard constant factors out in front. You have some terms which I'll talk about a little bit more in detail in the next slide. This 1 plus this q tilde sub z squared. You have this term that goes as this f of q, the form factor squared. You have this Debye-Waller term. And then you have 2 terms in this sum. And what you see here, you have delta functions in energy and q, and times some thermal factor. And this is not so different than cross-sections that you've seen before for phonons, but in this case, these are the magnons that you're scattering from. So the first term in this sum corresponds to magnon creation. So you're sending a neutron into your system and you're creating a magnon and it's losing energy. And the second term here corresponds to magnon annihilation, where you're sending a neutron into your system and then you annihilate a magnon that exists in this system and the neutron gains energy. And the different the different thermal factors here correspond to having detailed balance for those two types of excitations. So let me make a few notes about the cross-sections. So one thing, the magnitudes are roughly on the same order as inelastic scattering from phonons. So when you see some excitations in a neutron scattering experiment, you might have to do some work to differentiate them to figure out if one's magnetic or from a phonon. And since these are well-defined excitations from an ordered state, they will have sharp surfaces of dispersion, and we saw that we had these delta function-like excitations. But there are some interesting parts of the cross-section, and again, we saw that there's this form factor of the magnetic ion, F squared, which falls off with increasing Q. And this is useful. So this is one of the ways that you might differentiate magnetic scattering from spin waves from phonons is if you measure the dispersion relations in several Brillouin zones, and you measure Brillouin zones that are further out in Q, the intensities will change. They will drop off for the magnetic scattering, but for the phonon scattering, they increase with Q. So by looking at how the intensity changes with Q, you can have a better idea of what you're seeing as phonon or magnon. And there's also this orientation factor. So this 1 plus Q, I guess it's a hat, Q hat sub z squared. And this Q hat is just the Q vector normalized. And this orientation factor you've probably seen before as well. It comes due to the way that the neutron interacts with the spin. And for elastic scattering, you're probably familiar with the magnetic cross-section, or you'll get magnetic scattering from the ordered moment that's perpendicular to Q. And that has the same physics that what you're seeing here for the inelastic scattering from the phonons. So something I should note is that here Z is chosen to be the quantization axis of the spin. So if you apply a field, you can align that quantization axis in different directions for a ferromagnet that is. So what you could do is have a field aligned along your Q vector. And if you do that, then this Q hat will be 1. So you'll have a 1 plus 1 orientation factor, or you'll have a factor of 2. If you just change the field direction to be perpendicular to Q, then this Q hat will be 0, so this orientation factor is just 1. So you just changed your magnetic cross-section by a factor of 2 by changing the direction of a field, and clearly phonon scattering would not do that just by changing a magnetic field direction. You shouldn't change your phonon scattering, so this would be another way to distinguish magnetic scattering from phonon scattering. And I think I'm going to talk more about this orientation factor term as well. So you get this factor of 2 if you have the field along the Q vector because you have two transverse modes, and you're going to see both of them when the ordered direction is along Q, since you'll see the inelastic polarizations that are perpendicular to Q. So I'll talk more about that when we show some data. Okay, so let's go to some data. So here's some early neutron scattering results on, I believe, iron. There are many other ferromagnets also in this paper by the Brookhaven group. So this is triple axis spectroscopy, where they go to a certain Q vector. Oops, sorry, no, they go to a certain energy, in this case, and scan Q. And so these are constant energy cuts, and you can see these inelastic peaks. In this bottom panel here, you see two peaks, one labeled M, which is magnetic, and one labeled LA, which is the longitudinal acoustic mode. So you have both a spin wave and a phonon in the same scan. And when they plot the data, that is just due to this spin wave mode. Here, they show that what you have is a quadratic dispersion at low Q, and then going up to higher energies, it starts to fall off this quadratic dependence, which we do expect. But you also see that you do have this overlap with the acoustic phonons down here, so you have to do some work to distinguish the two. I mentioned some possibilities of what you might do, for example, measuring in multiple Brillouin zones and seeing how the intensities change with Q. You could also do things like polarized neutron scattering. And so these data were taken on large single crystals. So you can go to particular points in reciprocal space and cut through these dispersion surfaces. Now, if you don't have a crystal, are you out of luck? Because if you have a powder sample, you powder average all of the orientations, and it might be hard to extract information about these dispersion surfaces so easily. But there's a nice trick here. If you have a ferromagnet that's on a cubic lattice, and so what you can do is use powder samples to extract the dispersion at small q to get, for example, this D factor for the dispersion. And so here's some work done by the NIST group on the ferromagnetic state of manganite. And the idea is to actually measure near the 0, 0, 0 Brillouin zone. So you're near the main beam direction. You need to have good energy and Q resolution just to reduce your backgrounds. Now you can imagine that for a powder sample, if you were at large Q and looking at Brillouin zones away from Q equals 0, then you'll be mixing up zone centers with other zone boundary positions, and what you would measure if you scan energy would be some broad collection of excitations because you're measuring several Q positions simultaneously that have different energies for the spin waves. But near 0, 0, 0 for a cubic system, the dispersion is isotropic. So even if you average over different orientations, they're still at some fixed Q away from 0, and they will all have the same dispersion, this quadratic dispersion from the 0, 0, 0 position. And that's what they're showing here. So you see these well-defined peaks in this figure on the left when they stay at some small q, 0.07 inverse angstroms in scan energy. And then they can even change the temperature in this material and show that the spin wave stiffness changes with temperature. Okay. So a lot of the times having single crystals is the best way to measure these excitations, but sometimes you can get around that requirement. So that was for ferromagnets. So let me go to another quote-unquote simple case, the nearest neighbor Heisenberg antiferromagnet. And I'll write the Hamiltonian like so. And in this case, without the minus sign in front, for positive J, the rule is you want SI, SJ to point in opposite directions. And we can first think about what we expect classically. So if the rule is for spins to be in opposite directions, then you should just have an up-down state, which we call the nail state. And that's our classical expectation. But looking at the quantum operators, and again, we can write SI.SJ in the following form, we see that operating this on this up-down state does not produce some constant times that state again. This up-down state is not a quantum eigenstate. So it cannot be the true ground state. These antiferromagnetic systems are a little bit more complicated to think about in theory. However, if we just push on with the methods that we have used to calculate spin wave dispersions, we can get some basic understanding. So let's use the Néel state as an approximate ground state. And the basic idea is that you have two fixed sublattices, so one with spin up and one with spin down. And then you can apply spin wave theory on that system of two sublattices. And when you do that, the following result comes out. And now I've already reduced this to just having nearest neighbor exchange, 2zjs, and then the square root of 1 minus this gamma squared. And you see that you have this square root of this 1 minus gamma squared. So let's put this on a cubic lattice and look at small q. You actually get something that's very different in terms of the leading order behavior at small q, and it's going to be linear in q. So instead of being quadratic, it's linear, and here's a picture of what you might expect for having anti-ferromagnetic spin waves. All right, so let's see, does this work out in theory? Does this work out in a real system? Does the theory work? Here's some neutron scattering data on a spin 5/2, so relatively large spin, square lattice, Heisenberg antiferromagnet, rubidium manganese fluoride. So manganese is the magnetic ion here. This was work done by Huberman and Roger Cowley's group, and some people from Bob Bergeneau's group at MIT who I knew. So they did these measurements at ISIS in Rutherford Lab in England using the MAP spectrometer. So this is a different technique than the triple axis technique. And here, by time of flight and having a very large detector bank, you can very efficiently measure a large region of Q and omega space. And this is quite nice for these types of low-dimensional magnets, because you can integrate along the direction perpendicular to the square lattice planes and just enhance your signal that way. So some of the results are shown in these three panels. I guess this is the kind of artist rendition of what their data looks like, and there's a color code for the intensity. Here are some of the actual data. So cutting at different energies through these cones, you can see that you have these rings at some finite energy with, there's rings are almost like dots at very low energy down here, and at very high energy, you're looking at the zone boundary the zone boundary magnons. And this final panel here, I believe, was taken along this this green line in the middle panel, and you can see that when you cut through one of these cones of scattering, you get a very sharp peak. And again, these spin waves should be delta function sharp, just convolved with your instrumental resolution to give you the width. And I think it's very clear that you can see in their data that you do have something that looks like a very linear dispersion from the zone centers, which is different than the ferromagnetic case, but this is what we expect for the Heisenberg antiferromagnet. If you now look along different high symmetry directions and you plot the position in energy at different wave vectors, you get the following dispersion plots. And going from a zone center to some zone boundary in the first panel, you see that it does look quite linear over some region before it flattens out. Let me jump over here. As well, it looks like there is some linear region. One thing I want to point out, though, is that it looks like that this does not go to 0. And I guess it's not really clear in their data, but there are other results with lower energy data points that show that there is a small gap at the zone center. And so this means that it's not just the perfect Heisenberg model, that there's some additional term in the Hamiltonian, such as having a spin anisotropy. So you can modify your Heisenberg Hamiltonian in the following way. So if you just had these three terms with the same prefactors along the x, y, and z direction, that would be Heisenberg. But now you have some additional delta here for the z term. So you have a Ising-like anisotropy along the z direction in this magnet, and that will give rise to a small spin gap. But something that's quite nice from the linear spin wave theory calculation for just nearest neighbor exchange is it predicts there to be no dispersion along the zone boundary, and that is what is seen here. So this linear spin wave calculation for this relatively large spin square lattice antiferromagnet seems to work quite nicely. And there's another square lattice Heisenberg antiferromagnet that you may have heard of. It's very important in physics, condensed matter physics, lanthanum copper oxide. It is the parent compound of the original high TC superconductor. So when it's doped, it's a superconductor. When it's undoped in its pure form, stoichiometric form shown here, La2Cu04, it is an antiferromagnetic insulator. So here's the crystal structure for such a system. And the coppers are shown with these spins on these the small black atoms. And they're on a body center tetragonal structure, but it's really a square lattice of these copper ions. And to first approximation, this is a very good Heisenberg system. So J is almost isotropic, so that isotropic J is very large, about 140 millivolts. But if you look at low energies at the spin waves, you also see gaps. So that means there are some anisotropy terms, and these could affect the low energy physics. So this early paper by Peters et al., also done at Brookhaven, deduced two gaps, and one of the gaps they attribute to something that's here due to antisymmetric exchange, and I'll say a little bit more about that in the coming slides, also known as a Dalajinsky-Maria interaction. And another gap is related to there being some anisotropy, exchange anisotropy, like an XY-like tendency for the spins. So, what is the evidence that you have two gaps? So one thing that you can do is measure at the zone center. So these are up here, Q equals 0 spin waves, but they're going to change to component of what they call B star here. So that's the thing that's changing from panel to panel. And the way they define the axes here, so B on this crystal structure is the direction perpendicular to the planes. There's very weak coupling between the layers, so there should be very little change in the dispersions in this perpendicular to the plane direction. But the thing that is changing is this orientation factor that I talked about before. So now you can imagine for this case over here on the top, for Q nearly for Q nearly aligned along the B direction, so there'll be some small in-plane component, but with a large out-of-plane component. So if Q is parallel to the B direction, then you're not going to see polarizations that are parallel to that B direction. That is, you're not going to see fluctuations out of the plane. So you're only going to pick up in your cross-section the in-plane spin waves. So the transverse modes that correspond to in-plane fluctuations. And then as you start decreasing the Q vector, you will start to pick up both in plane and out of plane. So on the top here, they're claiming that only the in-plane mode is seen, and you can deduce some energy gap of about 1 millivolt. And here, you're not seeing a sharp peak, but you don't expect to. Again, the exchange is really large. It's 140 millivolts. So you're going to just see more of like a threshold for scattering, and then a lot of weight to higher energies. So it's this threshold that I guess that they're fitting. And then down here, there's some qualitative change in the way the scattering looks, and they deduce an extra peak around 2.5 millivolts. And maybe you're not convinced, but in the early days of high temperature superconductivity, making large single crystals was still an art. So these are very difficult measurements. Let me follow this up on another compound. So this is very similar. It's lanthanum copper oxide, co-doped with neodymium. This changes the structure a little bit. I don't want to really get into the details of that, but it is, again, a spin 1/2 square lattice Heisenberg antiferromagnet. And I think the data are a little bit cleaner here. And again, the idea is to deduce what are the terms in the spin Hamiltonian. And neutron scattering is a really powerful way of telling us that. So in addition to just the basic Heisenberg exchange J, we can figure out what are these small perturbations with some very good precision. So there's this alpha xy, which is telling us about the anisotropic exchange, and the Dioulogin-Schmier interaction over here, which is the anti-symmetric exchange. And the basic idea is the same. So this is work by Keimer and co-workers. They stay at the same in-plane Q position near the zone center, but they just change this direction perpendicular to the planes. So therefore, you can, at large Q, you're just looking at the in-plane fluctuations, and then at smaller QC, you're seeing both in-plane and out-of-plane, and you can deduce two gaps. And from this data, and there's another way to do this over in this panel. You could go to 5 millivolt neutron energies, and that will give you much higher energy resolution. And if you just look at this high temperature data, for example, you can see that you do have these two peaks here, and those two peaks do move as you cool down. And you can deduce what these anisotropy terms are. And they're very small, 10 to the minus 2 and 10 to the minus 4 in this important copper oxide material. Okay, so those are ways neutrons can tell you about terms in your spin Hamiltonian, but more or less looking at conventional spin wave modes that we expected from the Heisenberg model. So let me say a few words about something that's kind of new. You can get a new spin wave mode due to geometrical frustration, and this will occur on the Kagame lattice or other highly frustrated systems. The basic ingredient for having geometric frustration, for example, is having a lattice based on triangles. So you have your Heisenberg Hamiltonian, and you could have two of your spins anti-parallel with each other, but the third spin on this triangle can't be anti-parallel with both, and we say that this is a frustrated geometry. And there's a few more basics about this. So if you do have just Heisenberg exchange, there is a compromise state for each triangular plaquette where each spin forms a 120-degree arrangement with each other. And I've color-coded them, so I have a red, green, and blue spin that form this 120-degree arrangement. And if I put them on one triangular plaquette, and if this is an edge-sharing network, then the green and blue are shared with its neighboring triangular plaquette. So therefore, this other spin must be red in order to satisfy this rule. So for an edge-sharing network, one triangle constrains the entire lattice. If you have a corner sharing network, on the other hand, well, in this case, you only share a single common vertex with its neighbor. So red is shared, that's common. But between this system, or this configuration, and this configuration, I can swap the blue and green on the bottom two sites and still maintain this 120-degree arrangement. So this is a way of getting much higher degeneracy. And so for classical spins, you can have a huge degeneracy on these corner sharing networks, which is called a Kagame lattice. And the edge sharing networks we call a triangular lattice. Another way to think about this is in terms of a chirality. You can think about how do the spins rotate as you go around a triangular plaquette. And it turns out that you need staggered chirality for a triangular lattice in its ordered state. The Kagame lattice can support many different chiral patterns, and that's another way of saying there's a huge degeneracy to the ground state. So what's a consequence of this high degeneracy? And just looking at the Heisenberg Hamiltonian, on this interesting lattice, it turns out that you will get three modes, and two of them disperse, shown down here, as you expect for an antiferromagnet, so linearly from the zone center to some high zone boundary energy. But there is some interesting spin wave mode, which is called a zero energy mode, and it's completely flat and remains at zero. And that's very unusual. And that we can have some physical picture for, and it's shown here. And I tried to just draw how to picture this. You can think about taking an axis along this up pointing spin direction, and then the two other spins that share that plaquette, you can now rotate them in opposite senses around these dotted circles that I show here. And that will maintain this 120-degree arrangement for the three spins on that plaquette, and therefore do not change the ground state energy. But once you start perturbing these spins on this line, you have to perturb all of the spins on this line. So each spin processes in opposite senses. However, this line of spins is essentially decoupled from this line of spins because there's just a single vertex shared between plaquettes. So you can create arbitrary wavelength rearrangements along this direction going up and down, and that means in these different wavelength rearrangements don't change the energy, which means that as a function of wave vector, looking at this dispersion, for many different wave vectors, you have the same the same ground state energy. And that's the origin of this zero energy mode. So this is very unique, and it's characteristic for highly frustrated lattices. And that was predicted, when was that? Sorry, going back, 1992. And you want to see it we're experimentalists to look at it in real materials. But before we try to look for that, what do we expect realistically? Well, in most materials, we have spin anisotropy. You can imagine having some XY-like anisotropy term or some Ising-like anisotropy term. And if you add these types of anisotropies, you will change what the spin wave spectrum looks like. So instead of having this zero energy mode at zero energy, it becomes lifted. But an interesting aspect is that the zero energy mode is still completely flat. And one way to think about that is to think about the polarization associated with this zero energy mode. So the zero energy mode, the physical picture I showed in the previous slide was that you're taking a rotation axis along one of the spins on a plaquette, and the other two are rotating in opposite senses, like shown in this top picture. And this type of excitation wants to pull the spins out of the Kagame plane, so this has an out-of-plane energy cost. So you will now, and every spin along that line has to pay that cost. So you do raise your zero energy mode to some finite energy, but it does remain flat still. So that's where this lifting of the zero energy mode comes from, and the energy gap will be related to the XY-like anisotropy. So to look at this, we want a real material that has a Kagami arrangement, and a material called iron jarosite has these perfect Kagami networks of iron 3+, which has spin 5 halves. So what's nice is you have these single undistorted Kagami layers. You can make these compounds stoichiometrically pure, which are important. So everything I've been talking about is in the limit of essentially having zero disorder to get what the true ground state is in the absence of disorder. And the nice thing is that crystals can be made. Here's a picture of a very large single crystal that was made. And with neutron scattering, we want to ask, does this, it's essentially mineral compound, have an interesting Hamiltonian, and how would we know? So we did neutron scattering. Oh, so before going to that, we can look more, seriously at the crystal structure and, figure out, well, what do we expect for the spin Hamiltonian? So we do expect there to be some super exchange interaction. So these are the iron atoms in red, and there's this bridging oxygen atom between them, which can give us this J. But we see that the bond between the irons is buckled. So due to this buckling, what we say, there's not a center of symmetry between the magnetic ions, and therefore you can get what's termed the Dalachinsky-Maria interaction, and it goes as this D vector dot Si cross Sj. And this D vector is determined by the quantum chemistry of your crystal. And you can make some arguments about what the direction of the D vector will be, and it's going to point something like these two green arrows that I've drawn on this figure. So there'll be two components to it. There'll be a dy component and a dz component. And in principle, you could also have a further neighbor interaction for this system. So this dz, if you want to have this d dot si cross sj to give you a low energy, then having a dz vector added the Kagami plane means you want si and sj to both be in the Kagami plane. So this gives you an effective XY-like anisotropy, and it also selects a chirality. And then this dy vector, this dy component here, picks a particular in-plane direction. It gives you an Ising-like anisotropy. It also does some other things like give you a spin canting, and these are some predictions that we have measured. But let me just focus on the neutron scattering. So here's some inelastic neutron scattering from the single crystal of iron jarosite. We did this at Oak Ridge on HB1, and we did various constant Q and constant energy scans. And essentially for all of the different peaks that we measured, you just need 4 parameters: your Heisenberg exchange, your further neighbor exchange, and then your components of the Dalachinsky-Maria vector to determine all the peak positions. So we're looking here in this first panel at the spin wave peaks. This is at the zone center on the bottom, and here is slightly away from the zone center. You can see them disperse to higher energy. So we do have 2 gaps at the zone center. But what was very interesting was looking over in this right series of panels. So 110 is another zone center, and then as you go out to the zone boundary, you see that this peak has not really shifted all that much. It's nearly dispersionless. It's a very flat mode, and that was very interesting to us. So when we put all of our data on a dispersion plot, we can see that we do have dispersive modes, and those are shown in red. But what was very exciting to us was this blue mode, which is extremely flat. It goes from some zone center energy, and it doesn't disperse to a high position at the zone boundary, but it stays at a very low energy. And this is this lifted zero energy mode due to this ideal, Kagame highly frustrated geometry. And the lines in this plot that I'm showing you are fits to theory, and we can now extract numerical values for the exchange parameters and the leading perturbation, the Dalachinsky-Maria interaction parameters. So it's also one of the best characterized highly frustrated magnets. And again, having neutron scattering of the spin waves on a single crystal is the best, bar none method for characterizing such systems. Okay, and armed with that data, we can look at other methods that are standard or typically used to estimate J. And what almost all of us do in the field of magnetism when we first have a new system is to measure the uniform magnetization and also the uniform susceptibility as a function of temperature. And we could do this on a powder sample, which is typically what you have first. And if you plot 1 over the susceptibility, it usually falls on a line, which tells us you have Curie-Weiss, so inverse susceptibility, and that tells us we have Curie-Weiss behavior. And Curie-Weiss behavior means that you do have some interacting spins, and it's the high temperature behavior, so you're measuring this at high temperatures. And the conventional Curie-Weiss law tells us that your Curie-Weiss temperature, so the temperature here on the x-axis, this is negative 800 K, which tells us we have an anti-ferromagnetic interaction. So that temperature is given by the following 4/3 J S times S plus 1. And we would have extracted a J, nearest neighbor exchange, of 5.9 millivolts. But we have this neutron scattering, which tells us J is actually closer to 3.2. So just doing some simple analysis of the uniform susceptibility actually gives us a substantial error in the expectations for J. It turns out because this is a highly frustrated system, there will be modifications to the susceptibility at these temperatures. We're really not in the extremely high temperature limit, so there are some correlations here, but we still get Curie-Weiss behavior due to the frustration. And some series expansion calculations show that there are some corrections to the Curie-Weiss behavior, and if you just take the uniform susceptibility data, you get a J now that's 3.9. This is closer to the neutron result. Again, the neutron result is the correct result. It's the best we could measure. So this Curie-Weiss behavior is closer, if you apply the corrections that are lattice specific in this case. But again, there's no substitute for neutron scattering, which is the best way to understand the interactions in magnetic systems. All right, I'm getting close to the end of what I prepared for this lecture. So this is the second to last slide, and it's kind of a teaser for some of the things I want to talk about in the coming lecture. And I've been talking about spin waves in ordered magnetic systems, and you can ask, do all magnets order? There's a well-known theorem, the Merman-Wagner theorem, that says for a system with a continuous symmetry, you will not have a finite temperature phase transition to an ordered phase in D less than or equal to 2 dimensions. So for example, the 2-dimensional Heisenberg antiferromagnet or 2-dimensional Heisenberg ferromagnet should not order based on this. But I showed you a 2-dimensional Heisenberg antiferromagnet that had spin waves. It clearly had order as a ground state. And it's because in all the real materials that we've seen so far, they are 3-dimensional crystal structures, and they will have interactions along all 3 directions. So these are 3-dimensional magnets, and they do have ordering. Even though you might have stronger ordering in the plane, there's still going to be some weak non-zero coupling between the planes, which gives you the 3-dimensional ordering at some low enough temperature. So you might ask the new question then, in some real magnetic systems, which of them will not order, right? Because we know that at some level there are three-dimensional interactions, so they should all order, you might imagine. But some of them might not. And you might consider cases where you do have geometric frustration, where you can have a huge degeneracy of the ground states, and that will tend to frustrate ordering. You can think of very anisotropic or low-dimensional systems where the 3D coupling is very weak. Something that would be very interesting, and we'll talk about a lot next time, are low-spin systems where quantum fluctuations for the antiferromagnetic case are very strong. And combinations of the above. So if you can combine low spin with low dimensionality, such as spin chains, you can get very interesting physics, and neutrons have had a lot to say about that. Or if you combine low spin with frustration, you can get some very interesting physics as well. And again, neutrons are at the center of that type of research. So here are my conclusions, and just brief conclusions. This is definitely a discussion that we're going to continue. I just want to say that magnets are very good model condensed matter systems. Even if you're not doing research on this, I hope you understand that they are important because you have a collection of interacting quantum degrees of freedom, and how can that not be important? So the spin waves are, again, very fundamental to these magnets. They are the low energy collective excitations when the ground state has ordering. And they can tell you a lot. They tell you what the interactions are, right? It is the best way to know what those interactions are. And then inelastic neutron scattering is an ideal probe for the spin waves. Bar none, this is exactly the type of experiment you want to do if you are studying magnetism. So from that, if there are questions, feel free to type them in. Hey, well, thank you. Oh, question, all right. Are some of the gyrocytes multiferroic? Good question. The quick answer is I don't know. I mean, they do have things that you would like non-collinear ordering. I don't know if the electric polarization has been measured, so I don't know that. I don't know the answer to that. You're welcome.